Hello, my dear students. I'm Shrikala, faculty from the Department of Mechanical Engineering, Global Academy of Technology. Today, in this lecture, I'm going to discuss about forced convection. Before that, let us see what is convection. Convection is a mode of heat transfer occurring predominantly in liquids and gases with the bulk movement of the fluid particles. Normally, the convection is classified as natural convection and forced convection based on the movement of the fluid particles. In natural convection, fluid motion takes place naturally due to buoyancy effect. That is mainly due to density difference of the cold and the hot fluid particles. For example, here you can see a beaker getting heated. The fluid particles near this hot surface gets the energy in the form of heat, becomes lighter, moves on to the top surface. From there, it pushes the cold particles downwards. Again, those particles gains energy and moves up. So in this way, the circulation of the fluid particles takes place due to temperature difference in natural convection. Again, in forced convection, it is not so. In forced convection, the fluid particles moves or the motion of the fluid particles takes place due to external means. External means may be the fan or a stirrer as shown here. Now, coming to the law governing the rate of heat transfer, law is expressed by Newton's law of cooling. The law states that the heat transfer by convection is directly proportional to the surface area exposed and the proportional to difference in the temperatures of the surface and the fluid, where if we remove this proportionality constant, we get that as H. Write it as H, where H is the heat transfer coefficient. And heat transfer coefficient is defined as the amount of heat convected per unit surface area per unit temperature difference. And this is expressed in terms of watt per meter square degree centigrade. The value of heat transfer coefficient depends on many factors: thermophysical properties, mainly the density, viscosity, thermal conductivity, heat capacity. It also depends on the flow properties, whether the fluid is laminar or turbulent. It depends on the nature of the fluid, and also the surface geometry. Surface geometry, maybe it depends on the surface roughness, smoothness, etc. Normally, the value of this H lies between 2 to 25 watt per meter square degree centigrade for gases and 50 to 1000 watt per meter square degree centigrade in free convection. Whereas in forced convection, value of H lies between 25 to 250 for gases and 50 to 2000 in liquids. Now, coming to the dimensionless numbers and their physical significance. So first thing is we are going to discuss about the Reynolds number. The Reynolds number is nothing but the ratio of inertia force to the viscous force. And this Reynolds number is predominantly used to analyze the flow regimes. For example, whether it is in laminar or turbulent or transient flow. So if we substitute the expression, we'll get it as u infinity into characteristic length by nu, where u infinity is the free stream velocity or the velocity of the fluid flowing. LC is the characteristic length of the plate. This will be dealt in detail in the coming slides. And mu is the dynamic viscosity. This mu by rho is replaced by the nu, and that value is which is known as kinematic viscosity. For the flow or the plates, the Reynolds number If it is less than 5 into 10 power of 5, call it as laminar flow. And if it is in the range of from 10 power 5 to 10 power 7, then we call it as turbulent flow. The same Reynolds number, if the fluid flows through the tubes, if it is less than 2000, calls a laminar flow. If it is less than 5000, calls a turbulent flow. In between, it is a transition flow. Next is the Prandtl number. Prandtl number is defined as the ratio of kinematic viscosity to thermal diffusivity. So if we just substitute the value or substitute the expressions for this, nu is given by mu by rho, and alpha is nothing but thermal diffusivity, which is given as K by rho Cp. If we substitute, we'll get the expression as mu Cp by K, where Cp is the specific heat and K is the thermal conductivity. Now, the next dimensionless number is Nusselt number. Nusselt number is expressed as the ratio of heat transfer due to convection to heat transfer due to conduction. So, if we simplify it, we'll get it as HLC by K, where H is the heat transfer coefficient and LC is the characteristic length. This is a measure of the convective heat transfer, and for a given value of Nu, H is directly proportional to K and inversely proportional to the characteristic length, which is a significant length parameter. The next dimensionless number is Stanton number. Stanton number is defined as the ratio of wall heat transfer rate to convective heat transfer, or in simple ways you can say it is the ratio of Nusselt number to product of Reynolds number and the Prandtl number. So if we substitute and simplify, we'll get the Stanton number as H by rho U infinity into Cp. And this Stanton number is used only in the forced convection because we find the velocity component here. The next is the Peclet number. This Peclet number is a ratio of the rate of advection. That means it is nothing but the heat transfer due to convection by the flow to the rate of diffusion. So diffusion normally occurs, it may be heat or the matter of the same quantity. In a simple way, we can say Peclet number is the product of Reynolds number and the Prandtl number, where Reynolds number describes the flow regime and the Prandtl number describes the relationship between momentum diffusivity and thermal diffusivity. Peclet number is also used in mass transfer problems, where it is defined as the product of Reynolds number and Schmidt number, where Schmidt numbers simultaneously there is a simultaneous momentum and mass diffusion in convection in the Schmidt number. Next is the Grashof number. This Grashof number is generally used for natural convection, and it is defined as the ratio of product of inertia force and the buoyancy force to square on the viscous force. So again, if we substitute and simplify, we'll get the expression of rho square beta g delta t Lc cube by mu square, where rho is the density of the fluid, beta is the coefficient of expansion, and it is expressed as 1 by the mean temperature. Mean temperature means it is the mean of surface temperature and the fluid temperature. And g is the acceleration due to gravity. Delta T is nothing but the difference in the two temperatures, that is wall surface temperature and the bulk fluid temperature. And Lc is the characteristic length and mu is the dynamic viscosity. Now, as I said earlier, there is the term called characteristic length, which is the most important parameter. And it is defined as the ratio of 4 times the cross-sectional area to perimeter. So for the duct, for example, consider a duct flow. That means fluid is flowing through a duct. Then 4 times the cross-sectional area is given as pi d square by 4 divided by the perimeter. Perimeter is nothing but the circumference and it is given as pi d. So if we simplify, we get the diameter of the pipe itself as a characteristic dimension or the characteristic length, where ACS is the cross-sectional area, D is the inner diameter of the pipe. For annulus flows means where the fluid is flowing between the two concentric cylinders. For annulus flows, D is again given as 4 ACS by P. That means 4 into the area between the two cylinders. That means pi by 4 into capital D square minus small d square divided by the perimeter. Perimeter here, that means the surface with which the fluid is in contact. Now we can see here the fluid is in contact with the outer surface as well as the inner surface. So it is given as pi into capital D plus small d. And we get for the annulus flows, the equivalent diameter is capital D minus small d. Now, again for a rectangular duct, DE will be equal to 4 times the cross-sectional area by P. That will be equal to 4 times the cross-sectional area is length into breadth divided by the perimeter. Perimeter is nothing but the sum of the sides. So it will be 2 times the breadth plus length. Now, let us see how the boundary layer develops when a fluid flows over a stationary flat plate. Now, consider a real fluid or a viscous fluid flows over a stationary solid plate. Once the fluid flows in the form of layers, the fluid layer which is in immediate next to the plate surface will have zero velocity because the plate surface is not moving, it is stationary. And that layer which is in immediate next to the plate surface, layer of the fluid which is immediate next to the plate surface adheres to the plate surface, and that condition is known as no slip condition. That means the fluid layer will not slip off the surface and undergoes retardation. This further retards the layer next to it. That means the shear force is applied to pull the layer of the fluid or to reduce the velocity of the fluid. So in this way, each fluid layer next to it will have a pulling effect or the retardation effect. But as we go along the vertical distance, the effect of this plate surface reduces, and the inertia effect because of this flow, the free stream velocity increases and the velocity goes on increasing from 0 at the plate surface to almost equal to the free stream velocity. So this thickness wherein the fluid velocity increases from 0 to 0.99 times the free stream velocity is known as boundary layer thickness, and that layer is known as boundary layer. And within this boundary layer, the viscous effect or the shear effect will be higher. Beyond this boundary layer, that effect will be almost nil and the fluid will behave almost like an ideal fluid, and that fluid is known as potential flow. That flow is known as potential flow. Further, the downstream, as the fluid moves over the plate surface, the small disturbances downstream makes the fluid unstable and breaks it into turbulent boundary layer beyond the transition region. And if the Reynolds number is less than 5 to 10 power 5, the layer is known as the boundary layer is known as laminar boundary layer, and if it is beyond 5 to 10 power 5, it will be turbulent. And there will be, in the turbulent region, the smooth surface will have certain small roughness, and that roughness will be covered by a thin layer of the fluid. And within the layer of the fluid, the flow will be laminar, and that is known as the laminar sublayer. And this profile we see in the laminar region, the velocity profile in the laminar region will be parabolic in nature, and the velocity profile in the turbulent region will be logarithmic or the power law. And if we consider this plate, the place where the fluid, the entry point is known as the leading edge and the exit point is known as the trailing edge. Here, let us see some of the characteristics of the boundary layer. The thickness of the boundary layer increases along the length of the surface. That we have seen here, right? See, the boundary layer thickness is 0 at the leading edge. As you go along the surface of along the plate surface, the boundary layer increases. Till where it increases? Till the velocity becomes equal to 0.99 times the free stream velocity. Next is this thickness, the boundary layer thickness reduces with the increase in the free stream velocity. With the increase in the free stream velocity, the inertia effect will increase and the viscous effect reduces. Thereby, the Reynolds number increases. With the increase in the Reynolds number, the thickness of the boundary layer reduces. Next is, again, with the increase in the viscosity of the fluid, the boundary layer thickness increases because of the shearing effect. Next point is the shear stress reduces along the length. So after a certain distance, the shear stress or the viscous effect reduces, hence the flow becomes turbulent. And most of these flows are governed by the inertia force and the viscous force. If the Reynolds number is less than 5 into 10 power of 5, the boundary layer will be laminar and the velocity distribution, as I said earlier, it will be parabolic in nature. If the Reynolds number is greater than 5 into 10 power of 5, the boundary layer will be turbulent and the velocity distribution follows the log law or the power law. And the last point is, as I said earlier, in the turbulent region, if the boundary layer is smooth, the surface roughness, as I said, will be covered by a thin layer, and within the fluid within that layer will be laminar, and that layer is known as laminar sublayer. Okay. Next, similar to the velocity profile, there will be the temperature profile when the fluid flows over a hot or the cold surface. That means when temperature comes into effect. So consider now here in this picture, I am going to show a surface which is at a higher temperature than the free stream velocity. And the fluid or air or any gas flows over a hot surface. Similar to the velocity profile, the temperature also, there will be a variation in the temperature or the temperature distribution as shown in the figure. See, here we can see the temperature profile is going in this direction because here at the surface, since the surface is very hot, the temperature seems to be very high. As you go higher, the effect of the free stream increases and the temperature goes on reducing. It reduces till it reaches the free stream temperature. Since the free stream temperature is far less compared to the plate surface temperature. So that thickness is known as the thermal boundary layer thickness. See here the expression is given as the thickness of the thermal boundary layer is given by the expression below. Ts minus T divided by Ts minus T infinity is equal to 0.99, where Ts is the surface temperature, T infinity is the temperature of the fluid flowing, and T is a temperature at any distance y. If we substitute, if we get the 0.99, then that thickness y, whatever is given, is known as thermal boundary layer thickness. Similarly, here you can see the expression for, or the diagram which shows when the warm fluid flows over a cold plate. So initially you can see the temperature is very less because plate is cold. As you go higher along the vertical distance, temperature is increasing. So here it is Ts less, surface temperature is less. So as you go, this distance T infinity is higher compared to the Ts. So the velocity profile will be opposite to this profile as shown in this sketch. When the fluid flows over the hot surface, it will be like this profile. And if the fluid flows over the cold surface, the profile will be like this. And that thickness wherein the temperature changes from this surface temperature to the infinite or the free stream temperature, the layer thickness is known as boundary layer thickness. Thank you.